Board, share screen, screen one. Okay, here we go. So today we're kind of in a big arching thing. We're going to talk about binary math, WASM, Y, and gates and an OR, and we're going to look at an adder because this is the stuff that's coming next week. So today I hope to get through addition, subtraction, multiplication, and division, just to give you an idea of how it's all done in binary. Okay, so not too hard. And as a backup or I posted the link for this. This is that story of this fellow here, and it's interesting. You read through it, it's more about him as a person and the author's relationship, but he goes through here, and because he came out of school with an electrical engineering and discrete structures major, he ended up designing the chips for the Tomcat way ahead of Intel. So, and I thought this was an interesting article about why discrete structures is so important, because underneath discrete structures is your logic class you've taken and your assembler, your binary, ones and zeros. How do you manipulate the entire universe with ones and zeros? Yes, you can do it, but it's an approximation. It's not perfect, but this is just a fun article to read, and it shows the read only, and it was 20-bit words, and this is what flew the Tomcat, and there's a blow up of it. Now, how many transistors do you have in your phone? 9 billion. And so, yeah, there's a story about that. And then this one is the website to what I showed you of where this guy came up with it. It's got a 2-transistor computer, and it's working. Not fast, of course. But if you really want to learn the low level and you have an computer engineering slant, go play, go read, go explore, because there's a whole home-built PCs. There's a whole web ring of people that are designing CPUs in their garage, and that requires binary understanding. Okay. All right. So to start with, let's assume everybody has done the quiz. Nuts. Okay, no worries. We will go from there. So let me go to Canvas. You will find that I post in my classes a lot of work with due dates, but the due dates are way out there. Don't wait. Just get it done ahead of time. Give yourself a life, just get it done. Okay. So what I'm going to do is just bring this up real quick, and we'll talk about this. Look familiar? Yeah, this is the homework that you'll be doing, and this is just the process of making it happen. And let's see, how can I best do this? Let's use, right, that's not the one I want. Dang it. Let's use, should I use GVM? Oh, because I don't want my, I'll just use, I'll use WordPad, just because I'm on a Windows box and I can make the font bigger and smaller. So what we have here is 0 to start with. All I'm going to do is the binary decimal. So I have my 0000, when that kind of makes sense. We're just going to make it, 0000, right? So I need to make this bigger. Of course, it doesn't work that way. Ugh. Too low window. It's close. How about 20? Okay. So it's basically going to be 8. So I got my, whoops, one too many. 2 groups. All right, try to line it up a little bit. Okay. So that would be the first one. And the second one, that's kind of obvious, right? You're just going to you're going to flip 1 bit. Okay. I'll skip that one. This one, you can sit there and figure it out. Okay, what is 128 plus 64 plus 32 plus 8? 255. Now, why did I put that in there as 11111? So that equals 255. I'll demo. You can follow along if you want, but no, you can't. With 8 bits, 255 is the highest number you can represent. Now, why did I use that? Well, if I go here, this is all part of networking. Okay, if I say net if config, can you see that? 255, 255, 255. That's 8 ones, 8 ones, 8 ones, 8 ones. See the 1018 in front of it? 63, 99. And I used to be able to do it in my head, but you subnet these off and you can find the starting and ending IP address of that particular address range. Because the way this is notated, I've got 3 groups of 8. How many bits is that? 3 times 8 is 24. So in the world of networking, I would be writing this like 10.18.163. And usually it's a 0 here, not always. And then you say 24. What's that telling the network admin? That's telling the network admin that you have a broadcast address or a subnet mask of 255, 255, 255, class C. Does it have to be that? No. You can use 255.0.0.0. All these things, it's always a trade-off. We use class C around here because then you only end up with about 2,000, well, a little less than that, around 1,024 machines, 255 machines on a subnet. When you start making a subnet all in one big broadcast domain, things get really, really, really slow. Okay. Binary. How networking works. If you've done anything with HTML, your color codes, they're in hex. So what is what is FFFFFF in the color code? White. So what's 00000? Black. There you go. So there's another representation of binary. All binaries. Now, to find your starting and stopping IP address using the CIDR notation, as they call it, CDIR, you have to do a logic operation. You do an ANDing of the broadcast to find out what the next available IP is. Okay. All in binary. Okay. That's part of how it applies to you. And the reason I chose 8 bits is because of your network addresses, your color codes, the way things are laid out on disk, if you use Wireshark, so on and so forth. Okay. So 254 is going to be all ones except the last bit. Okay. And then 192. Okay. Basically, the way this works is wherever there's a 1, you add that value. This is an arithmetic way to do it. I will show you an algebraic way to do the same thing. Okay. I had a question in the 270 class of saying, why does mod 2 refer to, why do I have this monstrous big number if it's supposed to be a remainder? Remainder and modulo are not the same. Remainder is floating point. Modulo is integer. The best way to describe modulo is you got a series of buckets. So if I say modulo 2, I have 2 buckets. Okay. And I pick a number, whatever I want, 10, I mod 2 on that. Is it going to be a 0 or 1? So it's either going to be a 0 or 1. And that's going to tell me if it's odd or even. Okay. You can also use this divide by 2 modulo 2 in an equation to convert to binary. Okay. I don't know if we'll get to that today, but that's possible. But let's pick one that's a little more, one you can wrap your brain around a little bit, is let's say I've got 7,120 pennies, or yeah, 120, 70,000. Those are all pennies. Okay. And if I do mod 100 and divide by 100, this should be somewhat familiar. You know what? I should lower the desk so you can see. You're going to end up with a sore neck, you know. Basically what this does is it takes your pennies and it finds the fractional component, and then it finds, okay, that's what modulo and integer division do. No floating point here. Where's another place this shows up? Okay. It shows up, we used to have to do this the old-fashioned way. If I'm 125 days into the work week and I mod 7 it, how many buckets do I get? 7. Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Sunday, Monday, and then it gives me a number at the end, and then all of a sudden it gives me a numerical representation of the day of the week. Is it totally accurate? No. But it helps you understand what modulo is doing. Now, I may come back to this modulo idea when we talk about some optimizations on doing things, but that's basically all you're doing in this assignment. So I say 1 plus 2 plus 4 plus 8 plus 16 equals, and then I write it down in decimal, leading 0. Okay, because in the world of binary, 42, if, let me write these numbers down, 0, 42, and 42 are completely different. You don't have 1s and 0s at the number. So it's a wrong answer. So that's why I'm saying in the quiz, put the leading zeros on it so you get the right answer. Okay. And then to convert into hex, that's really simple. You just count, okay, 1 plus 4 is 5. So I got 5. And then I go down here, and so now I have 2 plus 8. Well, that's 10. But I'm in base 16. That's the letter A. Okay. This is all we're doing. We're representing binary and hex. And this is basically how most things are stored on the computer, in the computer, on the web, is lots of hexadecimal codes, because it's easier for the human eye to see hexadecimal codes. Because imagine a 64-bit address in all 1s and 0s, and you have to know that. and you have to duplicate that. So they shortcutted it and they turned it into hex. So that's briefly that. Okay. Now let's talk about our binary addition. Okay. Now addition in binary works the same way it does in decimal. It's just that when you have 1 plus 0 equals 1, but now I have a 1, 1. Uh-oh, I have a carry bit. So I put the carry up. Now I have 3 ones. What do I do? Well, it's a 1 with a carry. How many can see that? How many get that? I don't want to overwhelm you with this stuff, but the idea of understanding how binary works is step 1 on what is assembler doing. Assembler has basically these hexadecimal codes that get pushed into a register that do something. They turn on a light, they multiply, they add. So in your assembler, you have data and you have operands, and you have to say, okay, what am I going to do here? Okay. So we will get into programming assembler, and a lot of this stuff is going to leak out of your brain. Okay. I get that. But the idea is that once you've learned it and see how it fits, once you see how the Lego blocks go together, it'll start making sense. Okay. Now, I'm not asking you to be an expert. Now, here's an example. How many, when they go to, say, McDonald's to get their coffee, anybody do that? Or do you all go to Starbucks? I go to McDonald's and get the senior coffee because it's cheaper and it's got a good caffeine kick. Okay. But you go to McDonald's and say that'll be what? Let's say it's $1.12. And you give the person some oddball change, like a $10 bill and maybe 52 cents or something. And they don't know how to calculate the change in their head. They have to use the computer. I like to give change and dollars so I get the least amount of change back with the highest denomination of dollars. So if something's $2.50, I will give them $20.50. And they'll go, oh, what do I do? So that is not what I'm asking you to do in binary. Although what I just said is good practice for your brain. Okay. It's fun to try, try it. But so adding, so let's go through these. Now this actually has a way to show you how this works. And it's just doing an animation. And so it's doing that one. And then it goes to the next one. This is kind of slick. See how that's working? This is what makes binary so much fun, is that you can actually represent all kinds of things in binary. This is why DNA conversion, what we call digital to analog and then analog to digital conversion, is a big deal. This is how they convert, your heart and your heart sound waves, your heartbeat, into a representation that shows up on a computer. They have to sample it so they can get it to work. Everybody understand how sampling works, converting a sine wave into, anybody not know how to do this? See, you've got it, No, we got some no's in here. Okay. The way this works, let's see. What is my board showing? Now this is going to be really tiny on the camera, so all right, tough luck. Okay. All right, so let's remove this and we'll get this figured out up here. All right, let's say, oh, let me do this. Let me, I think I can get this to work. All right. It work? You may hear it? Okay. Yeah, let me just make sure. Let's see here. Yeah, it's probably not, probably can't get it to work. But if you play that on your computer at home, you'll hear this high-pitched mosquito sound. It's 14 kilohertz. It's a sine wave. That's all it is. So this sine wave at 14 kilohertz is one pure sine wave that goes like this. Yeah, that's it. How do I put that into the computer to make it an MP3? Anybody notice the difference in size between a WAV file and an MP3? Yeah. Some people tell me they can hear the difference. Well, I can't. But the way this works is you set up a clock. And you're familiar with this already. Your machine, your CPU runs at a certain clock speed, right? That clock speed is keeping your RAM refreshed with the ones and zeros in it. Because if you turn your computer off in the middle of editing a Word document, what happens to the Word document? Right? Ones and zeros, they need to be maintained with the type of RAM we have today, because we want RAM to be fast. It's not necessarily accurate. We have RAM errors all the time. But this clock is set at a certain timeline. And I won't go into great detail on that one, but basically they use a signal of around 44K or so. So every few microseconds of some determined length, it says, where is the value of the signal? Click, click. Where's the value of the signal? Click, 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 click. So can you see what's happening here is that we're taking a measurement of the sound from our digital to analog converter, our analog to digital converter. And this is represented in binary, ones and zeros. Okay. So I have a series of ones and zeros that are representing a close approximation of the sound wave. Okay. Does that make sense? Okay. All right. This is also how images are done. We take, okay, I'm going to take a picture and I want to get, okay, it's too big, let's make it smaller. So if you look at the guts in a hex editor of an image, it's just all ones and zeros, but it looks like it's all hexadecimal barf all over everything, but they all mean something. Okay. But this is how we convert into MP3. All right. So this is addition. So let's do an addition. Okay. Let's take two numbers. Let's just take a variation of what we see there. All right. This fundamental piece of taking analog into digital is called discrete structures. Okay. This is why software never fits the problem domain perfectly. Your software looks like this because of all of its discrete edges. Okay. It's very, it's just the way software is. But we as humans, I keep doing this, I keep moving them. Our problem domain looks like this. Okay. It never fits quite in the box. So when you get a new system for a company, you have to change the company policies on how they do things to fit within the boxes of the software. And you usually end up with a rebellion. No, I don't want to do it this way. This is the way we've always done it. Change is hard. Okay. Get used to it. All right. That piece of the puzzle of discrete structures is foundational. Okay, so we're going to do a quick add here. Let's do this one. Let's do a 1 0 0 1 and a 0 1 1 1. Okay. So using our little diagram. Now, I'm going to assume your silence is consent. All right. Yep, based on the number of bits that are in here. So can you imagine trying to remember a pattern of ones and zeros? Yeah, it'd be a bit tough. Okay. All right. So let's add this together. So we have 1 and 1 is 0 with a carry. 1 and 1, 0 with a carry. 1 and 1, 0. And now we have 1 and 1. And basically now we move it into another register. How many follow that? Okay. How many are having trouble with that? Okay. I'm here on Tuesdays. Come by and see me. We had a great time yesterday. There was about 5 or 6 of us showed up, and Helen brought in donuts. You guys missed a treat. Okay. So this is multiplication or just adding. Okay. All right. So it's telling you how it works. And here's an example of subtraction. The same concept. So let's watch our little video here. Okay. And it shows you what it's doing. And notice what they're saying here, 10. You know what that means? Versus 2. That's the base, or the buzzword is radix. So this is base 10, this is base 2. Okay. Sometimes you see it notated with numeric. Okay. But it's showing you how to subtract 6 from 7 in binary by converting it, and then you subtract it and you end up with that. Okay. Can normally be done by hand, but this is what's so cool. Subtraction can be done by determining the 2's complement representation of maybe -6, and then adding. All operations in binary can be reduced, if you want to say that word, into adding. So you can make things go a lot faster. Imagine doing this in a program where you have to sit there and say, okay, I'm going to subtract, subtract, subtract. Okay, let's write another program. We just flip all the bits and then we add. Now you only have to have an adder. With an adder logic gate, you can do addition and subtraction. Did anybody ever learn how to do subtraction in base 10 with addition? I didn't think so. Okay. I have not met anybody in 20 years who's done that. Okay. But this 2's complement is the way it works is you're doing this. So what's happening is you're working from right to left. Okay. And you just kind of flip the bits. Okay. And so here's this is the addition, and then we have to show you that. But that's what 2's complement does, is you are simply taking the second digit and flipping it. So you're turning all these to 1s and these to 0s, and then you're adding. Okay. That's basic. A shortcut way to think of it. It's not perfect. That's not the best description. Okay. So we're going to add 2 numbers. Okay. Let's take a look at these guys. So if we take these 2 numbers and so this is going to be is it going to let me do it? Pardon? Oh, start. Oh, that's right. Thank you. There we go. Here's our carry bit. So we can pick our number. So what number should that be? 1. So here we go. Any carry? No. And then we have a carry. We have a 1 and no carry, 0, 0. So here's our 32-bit number. So if we say 1 plus 4, what do we get? You got that. Awesome. Okay. All right. Now, overflow conditions for addition and subtraction. This is also part of the binary problem. What happens when you run out of registers? Okay. All right. Let's it's down here, I guess. Yeah. So here's what's happening here. It's showing you what happens when you have an overflow and you end up with this negative number. Now, this does show up, this negative number. Now, the way binary represents negative numbers is, let's take our 42 here, which is what? 0, 16, 0, 1, 0, 1, 0, right? 8, 1 more. 1, 2, 3, 4, 1, 2, 3, 4. Yep, there's 42. There's my 2 there. If I was to make this a negative number, I put a 1 in the highest order bit. So this is the way we flag negative. So we don't have a true 8 bits. We only have 7. And we're doing math on 7. And when that high order bit is flipped, we know it's negative. Now, on 8-bit, that doesn't make a lot of sense. But on 32-bit, it does. That's where this negative number comes from, that's how you represent the negative, is that 1 at the top, okay? Or you'll see it in print as HO, high order bit, okay? All right, and now there's how the adds and subtractions work. We'll get to that next week, okay? Now for multiplications, no, it can be negative. You just have to make sure that you are working with the 7-bit numbers. It can be anything you want, but what's your registers on your machine? 32-bit or 64? 64. So you've got that high order bit. So you're actually using 63 bits for most numbers, for most calculations, which can get to be a pretty big number. How about you remember the ancient days of Windows 95 and Windows 98 and Windows Vista? You had a problem with how big you could make a file. Anybody remember how big that got to be? 2 gig. Yeah, and you were stuck. You couldn't go any further than 2 gig. And let me find that number. What's that look like, folks? How many bits is that? That's why you had a limit on how much you could put on disk, is because of how many bits were available to write out the addresses onto disk. Oh, there's, I won't say this is absolute. Generally speaking, in a register of numbers, they always only represent one number. You're not going to have 2 numbers represented in that. Does that make sense? Or did I answer your question correctly? Or did I understand your question correctly? Let's start there. Depending on the math registers you're using, your ALU, arithmetic logic unit, that's where this negative comes in. Oh, why is it that high? Because you say 1, 2, 4, 8, 16, 32, 64, blah, 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 blah. Powers of 2 all the way up. Power of 2, yeah. And the algebraic thing to remember, should always just look on the desk. I used to teach binary conversion with this, but it confused everybody. 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, ad nauseum, or 2 to the nth. Okay. All right. Now what's 2 raised to the 0? 1, 0, 1. 2 raised to 1. 2. 2 raised to 2. See the pattern? So using this algebraic way, this is what threw everybody. 2 to the 0 power. What? You can't have 0 power. And I'm like, it should be 0. And I'm like, in math, you can prove addition. You can write a proof to prove addition. When it comes to subtraction, we accept it by definition. There is no formal proof for subtraction. Okay? You'd be a gazillionaire if you figure that out. Okay? All right. So the overflow, now you're gonna, oh, now what do we do? Okay. Now, anyway, arithmetic. Now we're getting into multiplication. And multiplication is just like we do it now. So 1 times 0, 0, 1 times 0, 0, 1 times 1 is 1. And then we go 0, 0, 0, 0. So you see the shifting? Now what happens if I collapse that and shift the whole thing over? So what do we do here? Okay. So this is a way to do it on paper. Okay. So let's just watch it. And it's giving you an explanation down here. So as I'm doing that, and then you can see how it's moving over. And then you add them together. Okay. Now you, these buzzwords, multican and multiplier, you'll use for this class and then you'll forget it. Okay. But the concept of what's happening when you multiply, you kind of want to know that. So here's how it works. Okay. All right. This is a 32-bit multipan and multiplier. Okay. And basically, this is how we would write the logic using gates to do that. Okay. And we'll talk more about that next week. Okay. And so here's the flow chart of how we're doing it. And then we shift it. And then we go through and we say it's done. Okay. Now here's the refined version. The refined version is using shifting to multiply. And then basically you shift and then add. Okay. So there's basically, that's kind of how it's working, is we're doing some shifting in here. And when you work on this stuff, don't get overwhelmed by getting every single point right. Okay. There's way more content in this book that we're using than we're going to cover in the class. There's going to be some stuff I'm not going to spend a lot of time on, like matrix multiplication. I don't want to break your brains this early. You know, I don't want to chase everybody out of the room. The idea behind this part of the class is so you can see how all the ones and zeros and the logic gates relate to writing code in assembler and then getting assembler programs working. Like, how do we do the hello world? It's a lot harder than assembler. Well, how do I put the H into a register to make it print? 35 steps. Okay. How is it in Python? Print hello, you're done. Okay. All right. And division, the way they're showing it is this way, and it's doing the same type of thing. Okay. So let me hit play. Whoops. There we go. So you can see what it's doing. So it's just like what you've learned in decimal. It's just only using 2 digits for everything. Run through this 4 or 5 times to kind of let your brain percolate on it. And I've had this discussion with, since COVID, this discussion comes up way more often. When you're trying to learn something, turn off distraction, set down your cell phone, turn off your music, put earphones on, whatever you need to do to make it quiet, and then concentrate. Okay. Because if you have a gazillion distractions, it destroys your ability to focus. I've mentioned that, I think, in class. And then one of the things that came up during Justin's talk was handling stress. One of the fastest ways to reduce stress, take a deep breath and pretend you're blowing out a candle. And do it as long as you need to. Do that 5 or 6 times. And that forces there's a sympathetic nervous system, fight or flight, and then the parasympathetic, rest and digest. That forces the parasympathetic to fire up by just doing a long, slow exhale. Okay. I have other yogi techniques, but won't go into those. Okay. All right. So this is the division side and divisor, quotient. These numbers are the same. And now they're talking about the how this works in the ALU. This is 64-bit now. They're explaining it, and then they have the flow chart. They're going through this, okay, and then creating an algorithm that works all the time. Okay, how do we do this? All right, and then they have the improved version where you're doing the shifting. And then they get into, what does this look like in assembler now? Now, this is RISC-V. Now, on my labs, this bottom one, RISC-SIM, is an actual online RISC assembly language simulator. So you can play with the RISC-V chip without having to buy a RISC-V chip. You can play with an assembler. So you can take some of the code that you see in the book for RISC-V and think, oh, how am I going to do this? Notice these funny little terms here. Add X5, X6, X7. Okay. Subtract. Add. And we'll get more into this side of the stuff over here. What does this mean? Okay. All right. And then floating point, I'm not going to go into a lot of detail on this one, but floating point is how do we deal with very, very large numbers? And there's some very interesting history on this. How many remember the atom bomb from Hiroshima that went on Hiroshima and all that? The computers in those days were not very accurate. So the story goes that when started in the 60s and 70s, when Seymour Cray started writing these high performance computers to model explosions, floating point math wasn't that good. So they never knew exactly what the right answer was. They had to make some educated guesses. And I happened to hear many years ago, Edward Teller, before he passed, on a Larry King show about his work on the bomb. And he was very reluctant to talk about what he did with the bomb. And but basically, Larry King started asking questions about math. And was a very interesting discussion of why America's losing good math people because we don't teach it the right way. And he had his own view on how to teach math. And he says, when the math works, everything works. And he just went on and on. He said that about like 900 times. When the math works, it's going to work. So he had very high confidence that when they blew up the bomb, it was going to work. And there were worries that it was going to split the atmosphere. They never knew that. And if you do some research on Starfish Prime, this is when they were doing above ground nuclear testing in the early 60s. My stepfather-in-law used to be involved. I think he was involved with this project. Never said. I just making a conjecture here. But when they set off the bomb, 300-400 miles away out in the Pacific, the radio stations in Hawaii stopped working. It was a giant EMP, electromagnetic pulse. They did not know that the atom bomb would create an EMP. They did not know that. That became new information in the early 60s. And how long have they had the bomb? 45? So, you know, the math they assumed they thought they knew, but then they saw an experiential evidence of going, oops, we missed something. That happens in science all the time. Okay. Yes. Yeah. And then the thing is with EMP, you don't have to take out the entire city. You just blow a bomb off, 3,000, 8,000 feet above the city, knock out the grid. You keep the infrastructure, basically radiate all the people. So now bad guys can do that. And won't get into how to make a bomb. You can actually find that in Reader's Digest. How I Made an Atom Bomb. I believe it was in the early 60s, late 70s. He actually wrote an article. You probably have to search pretty deep. You might have to go to a real library and look at an actual hard copy to find that. Okay. But floating point has been a problem for a long time. And once the problem is the way you have more than one way to represent floating point in binary math. You can do it this way or you can do it that way. There were no standards. So part of what created this is right here is they created a standard for floating point. How many have seen that fun movie Office Space? Okay, one person. If you haven't seen the movie, go see it. You can find it free. It's really funny. It's clever. And in essence, Office Space is about Y2K. Most of you were probably running around in diapers in Y2K. Okay. Well, I lived through it. And I can tell you this. No, the planet wasn't going to collapse in on itself like some conspiracy theorists let you believe. Airplanes are going to fall out of the sky. The biggest problem when Y2K was COBOL and the way they stored their values. You had a 2-digit year. They never thought the code they wrote in the 70s was going to last through that many years. Well, there's billions of lines of code in COBOL. So when you went over to 00, COBOL defaulted to 1900. Can you see what that would do to somebody's payroll check? Shipping, receiving, aging, AR, AP, headache city. Well, we made it through Y2K because a lot of dedicated people worked really, really hard behind the scenes. And we at Foster's, we found machines all over the enterprise that would not pass Y2K. Their internal clock, when you flipped it, they just shut off. They wouldn't boot again. One of them was a machine that ran the freezer. I can't remember the amount at the time, some millions of dollars of frozen inventory would have had to been hauled off and dumped because that machine would not cross over Y2K. Y2K became IT's best friend because it gave us the excuse to update everything in the enterprise. We got really good stuff updated, and it was really cool because we could have ancient stuff. Finally get rid of this old dinosaur, So in that respect, it was great. But living through it, I would not want to go through it again. The next problem in this is year 2038 with 32-bit registers. The date doesn't roll over. Why? That's your problem. I'm gone by then. Oh yeah, and then they're going to run out, and then that'll be fun. They got to go figure out how to reset it, and let's create another map. But this is a real story, and yeah, it's because in the early days of COBOL, you didn't have that many registers to store data. Okay, they had 8 bits and 16 bits, and that was about it. Okay, and then you'll see this, especially in JavaScript, NaN, not a number. Okay, what happens is it shows you how to, where these decimal floating point. I'm not going to go into great detail on these. Just kind of learn it, get in your head, pass the quiz, and move on. Okay. All right. And then they're showing you the floating point for RISC, the assembly language, and this is basically pseudocode, but basically it's kind of a C-like thing, and it shows you how it works and how to do it. And then now we have, this is in more of a, see, this is a matrix. Okay. Now I do need to mention something about matrices and vectors. This is kind of a big deal. A matrix is, I'm just using a 3x3 matrix, okay? A 3x3 matrix requires 3 axes. You got, so let's say it's got, a depth of 2 or so in there. So we've got a 3x2 matrix, okay? 3x2, but 3x3x2, okay? In memory, we can represent address spaces for this. That's a lot of address spaces. So what they do to speed this up is they vectorize the matrix. And basically what that does is it flattens out the matrix to be like this, okay? And now you have this vector that just screams for calculations, okay? Now, the mechanics of that, I'm skipping over, but this is basically how you would populate a 2x2 matrix, okay? And what you put into it, and then how you get your result, how you multiply matrices. Anybody multiply matrices in their algebra classes? A couple of you, 2 or 3 of you? That's what this is, okay? All right. Now, on that note, I'm going to stop here and we'll move on to the next thing. Now, what I want to do is introduce some stuff that is related to your future IE jobs. But right before that, I want to mention this. Yeah. Good for you. Yeah, it's that's exactly the point that I'm going to make. Is in math, computer science, what's the requirement for math? Calculus. Why? The reason you take calculus for a computer science major is so you can translate into code. You don't have to become a math god to finish your computer science degree. If you want to get into data science and algorithm creation and how to write quantum proof algorithms, yes, you're going to need to be a math god. Okay. But I never used calculus in all my years. Well, yeah, in recursion, yeah, in that respect, yes. Lambda, that's just recursion. It's a fancy name for recursion. Tail recursion. Yeah, I use that. Use that. That's great, except in C and Bash, if your inputs are too big, stack space overflow. It's a great way to pop a shell. But that's why you do calculus. Given the choice, I used a ton of stats. Stats you can apply to a job as soon as you start working. For example, I was asked to create a report. This is so stupid. Profitability by head count. Huh? So I got timesheet data and I got worksheet data. I got inventory data. I got mileage data and I got this data. And then I got total invoicing data and I figured out profitability by head count. Well, I was in the top 10. How'd that happen? Who wrote the code? I saved my own butt. Okay. So there is an advantage to having your finger on the pulse of the company. You may never make the money the CEO does, but you also know when they're lying. Okay. It's really, I always liked being in that position. I didn't care. Once I got to a certain point of living, when we were first married, we were pretty poor. We were situationally in poverty. And I told my wife, said, we'll be rich when we can buy orange juice whenever we feel like it. Live below your means, you will always have enough. Okay, it's that simple. How many people do that? Oh no, I've got a credit card. I can go all the way up to the top, $50,000. I'll get another one, another $50,000. And now you're in debt up to your eyeballs and you can't get any more money and now you're stuck and you don't have any groceries. Okay. So if you live below your means, you always had enough. Okay. Now let's talk about the thing I want to bring to the table that is related to assembler, and it's going to be in your future. I won't. WebAssembly. How many have heard of this? Not heard of it? Okay. So this is a new term. Excellent. Write it down, learn about it, and try to wrap your head around what it's doing. This is the, pardon that. This is the practical side of the assembler we're learning. Okay. What is this? Okay. Let's talk about our standard CPU running some assembler code. Okay. So here's my box and I have my input, my output. I got a CPU and I write the assembler and it runs where? Actually on the CPU chip inside of my box. Okay, that's what it runs. So it's running right here on the CPU. Okay, now let's abstract this out a little bit. Your browser. Go ahead and bring up your browser in front of you. Bring up Google. And I think it's under more tools and go to developer tools or Control-Shift-I. Okay, Control-Shift-I in Google should bring you to developer tools. How many have never seen this before? How many are not admitting it? Okay, the developer tools in Chrome let you inspect. Here's my Chrome browser. This thing is called V8. The V8 browser. Okay. This is where JavaScript runs. This is where all the magic happens in the world of Chrome. Okay. But basically, it shows you all kinds of neat little trippy things. So I can look at the console, and I can write code, sources, where it's coming from. I can look at the network to see how long it takes to do something. I can look at memory, Lighthouse. That's really cool. I like this Lighthouse. That's a great little tool for web devs. It tells you if you're standards based or not. It's a handy tool to have. And it's only HTTP Chrome extension navigate. Okay. So Lighthouse sources, where your data is coming from. But what am I looking at here? I can do a record. I can actually record all sorts of information, surf and save it. If you're going to be a full stack web developer, you're going to need to know that. Because this is how why is my page load taking so long? Well, you open DevTools and look at memory and go, oh, I'm downloading this 500,000 line JS package to make this pretty little widget. Maybe I don't need everything in the kitchen sink for that. Maybe I just need a subset of that. Okay. jQuery is an example. Huge. It's got everything in it. Do you need everything in it? That may be up to what you decide. Okay. But that gives you this V8. Okay. Now let's take this WebAssembly. It's kind of like a box inside your browser of choice. It does not matter which one. For the most part, all the modern browsers support it. But it's a virtual machine, a virtual box inside the browser that's running this WebAssembly. Okay. The website I brought up, why WebAssembly belongs outside the browser, it gives you some ideas of where things would go. Ponder this. Your Microsoft Word document. You bring up Microsoft Word on your PC. It runs an executable. It runs your C, whatever it is, probably C#. It gets translated into assembler, and then it runs on the CPU on your PC. What would happen if I recompiled Microsoft Word to WebAssembly? I could now take Microsoft Word and put it anywhere in the cloud. Everything we've talked about, virtual machines and Docker and Kubernetes, think of it as this. This is not a perfect representation, but for the sake of argument, it will be close enough. Okay. I think blue will work. If this is my CPU, I'm running ASM on my chip. This is the cloud. I'm running WASM wherever, doing whatever. Now, all I need is a browser somewhere. I don't need Windows. I don't need Mac. I don't need Linux. I just need a browser. That's it. Okay. This has got some very interesting future. I want you to notice something here. And if you want to write a game, look for a language that supports WASM, and then you can put your game right on the cloud. You don't have to worry about creating a separate distribution for every single operating system. Are lights going off? I hope they are. You know, because this is truly the future. Okay. And I've been in this game long enough. I can see trends, and I can see how great ideas just get recycled. This is one of them. Okay. But I want you to notice the little hourglassy looking thing means they're working on it, means it works, and means it doesn't. Okay. But I want you to notice C# and .NET. It supports all of the, you can run it in the browser. Other is the ability to do things outside of the browser, i.e. get to the hard drive. And the WASI is kind of a way to create APIs, okay? C++ is there. Ruby, C, Swift. That was a surprise to me. R runs in the browser. This is not a surprise. Go, Kotlin, and Rust. That's also not a surprise. When you play with Rust, Rust is a tough language to learn. Steep learning curve. But again, once you learn it, you can do anything you want. But it actually, you can write Rust code, compile to WebAssembly, and just send a WebAssembly package out and be done. There's some real future there, okay? And Go, I've been playing with Go, and it's kind of growing on me. I'm like, you know, this is kind of nice. It's more what I do, more the low level stuff. I don't do super low level stuff, and I don't write web pages for user consumption. I do networking stack stuff, and Go has got a really nice use case right there. Okay. And then these are some WebAssembly specific language. I've never heard of these. New. And other notable languages. Really? So you can run Lua in the browser, but not on the CLI or the WASI. Okay. Lisp, nope. Erlang, nope. COBOL? What? COBOL on WASM? Brilliant. There's billions of lines of code in COBOL. Imagine your Visa card. You go to a gas station. How long does it take to get it authorized? Less than a breath, right? Well, unless you're like most people, you breathe like this, like you're panting all the time. That means you're stressed. Exhale. Okay. Empty out your lungs. We wouldn't use credit cards if it took 2.5 minutes to validate a transaction. We'd use cash. You want to make cash king? Slow down your credit card transactions, and people will immediately start using cash. Yeah, inflation, blah, blah, blah. We can go into a long discussion about that, but I can say this much. All the way back to the time of Egyptians, there's been annualized inflation of 4%. So if you're in a capitalist society, 4% inflation is just the way it is. Okay. It had been artificially kept low for decades. And COVID hit. All of a sudden, no more artificially keeping inflation down. It's just the way things are. Don't panic. When I started using an ATM machine, I could get a single $5 bill out. And you're all laughing. Now I go to an A2 machine. It's asking me, do you want that in 50s? So, yeah, inflation has always been with us. It's just when it climbs a little faster than normal, everybody freaks out because it makes a great story. What were we saying about story? Learn how story works because you're being programmed by the stories you listen to. Program or be programmed. Okay. All right. That's that piece. Now, where's my notes that I have up here? Oh, here we go. And then I want to show you this tool. Now, this particular tool is, I would consider alpha. Windows, why can't you work like Linux? Notice where it is. Does it cost you anything to play with this? On GitHub? No. This is a WebAssembly Edge Compute server in beta, can use to be for production workloads with the appropriate testing. It talks to a server-side WebAssembly server, and then you have a WASM on the client. Think Amazon Ring doorbell. They are using an embedded system. I'm not sure who does it, but I do know that their scan guns that they use at the Amazon warehouses are all running a variation of Tiny Linux or Tiny Core Linux. It's a full distribution that runs on 10 megabytes. Your resume takes more memory. So look up Tiny Core if you're interested in small distributions, okay? But this, imagine having the ability to put an update on Ring computers or Ring doorbells across the planet in a matter of minutes. Rather than like what you do now when you have to update your firmware. You download it. You got to boot your system a special way. Then you hit the file. Then you upload it in the firmware, your firmware to your microcode, and then you hope to God that there's no problems, and then you reboot. This is why people don't update their home units, their home routers. It's hard to do that kind of update for Joe Average. But if you put WASM in Linksys routers, you can push out the change right there. I was talking to a former student. He is their lead developer at Comcast for SecOps distribution. So he's in DevSecOps, and he writes exclusively in Go, and he does exactly this sort of thing. He says, yeah, I have to write, once I get the vetted code, I make sure it's there and I package it up so they can push it out to all our clients. How many clients does Comcast Xfinity have? That's pretty cool. That's this stuff. So, do you want to be the person that helps people fix their shortcut on their desktop and then teaching them how not to use the coffee holder that's built into their computer, right? Or do you want to be on the next side of things? Which is harder to get to, A or B? B. It's just a choice, and it's just practice. That's the beauty of this profession. You don't have to be a genius. For God's sakes, I wouldn't be here. It's just a lot of practice. And like I've said before, I've just made more mistakes than you have. I've been around longer. I've blown up my share of systems. Long stories go here. Okay. All right. Now the other one is I want to bring this up just as an FYI. Now this is completely off topic. This was done not too long ago, but I heard of edX.org. If you haven't, write it down, go look at it. It's a bunch of free stuff. I mean, tons of free stuff. You do not have to come to college to learn stuff. You have to come to college to get units, get a degree, get it out of the way, get it done and over with, and then learn what you want to learn. edX, Coursera, Udacity. But edX just got purchased by a commercial LMS vendor for how much? Big payday. And I can tell you, edX is a nonprofit, and there's not that many people in the corporation. Okay. But you click on this one here, they discuss the future of higher ed, and it's an eye-opener. So here's the problem. Foster Farms has a policy of a 4-year degree for their higher end jobs. If you have your master's, that means this much more money. If you have an AA, it means this much money. So what's the degree used for? Base salary starting point. I have students coming back to get their degree because they can't get into management because they have to have a 4-year degree. If you want to shortcut that process and get a 4-year degree, yeah, I can show you how. Because I am a non-traditional learner from the get-go. If I go here, correspondence course, I got little packets, and I would read the packet, answer the questions, fill out a Scantron, mail it back. I'd get the answer. If I passed, I got the next packet and continued on. Not one unit transferred, but it got me my first job. My AA was a very scenic route through Modesto JC, Merced JC, Stan State, and I basically got my AA degree here without taking a single music class. I transferred them all in from Stan State. You don't have to play by the rules if you know what the rules are. Okay? If you understand how the academic system works, read the catalog and figure it out. Counselors are going to tell you this rubber stamp thing. Okay? I had a student come into me and he was really distraught. He's off making who knows how much money now. He moved to Salt Lake. Great student. But he said, yeah, my counselor said I'm not going to do much with an AA in computer science. Says the counselor who doesn't even know what programming is. So you want to talk to the discipline expert when it comes to degrees. Okay. Now, sometimes back in the day when my dad was flying airline, they didn't care what your 4-year degree was in. Could have been in music, could have been whatever. It had to be a 4-year degree. Well, now they want you to have a legitimate degree in the sciences. Best West, or not Best Western, this is Western Illinois Governors Institution. It was called Western Governors University. Every single unit was taken at other colleges and transferred in. My only requirement was I had to take 20 or 30 units from their institution. And because it was accredited in Illinois, I had to pass the Illinois Constitution test. And here's how those classes worked. You had a semester. They sent you a book and a bunch of VHS tapes or cassette tapes and say, learn it. You took one test and that was your grade in the class. At first, I hated it. By the end of it, I loved it because I could do it my way. It was great. And when you take the high stakes test like that, it's very much like a certification test. They basically pat you down and make sure you are who you are, and no calculators, no nothing. And you get given a pencil, and then you sit down and take the test, and they put it in an envelope and send it away. Western Illinois, that was, or this one was a at North Central out of Sacramento. This was every other week for 3.5 years. Foster's paid for it, and I got my MBA in leadership. I've said that this was not that hard, not at all. And this one was online, North Central Applied Computer Science. Take classes, just kind of like online. You do your work, turn it in, and get it. And the second one is in Applied Computer Science. It's supposed to be a PhD, but life happened. Okay. You do not have to follow the usual pattern if you don't want to. So if you want to go outside the edges and you're interested in different ways of obtaining the degree, let me know. I can show you ways to do that. Okay. And on that note, I'm going to stop yammering. So did the sign-in sheet get around? Nope. Okay. All right. Here's the sign-in sheet. All right. On that note, we can call it a day, and I'll turn off my